Hello everyone, my name is Matthew Perez, and today I'll be presenting my Interspeech work titled Aphasic Speech Recognition using a mixture of speech intelligibility experts. This work was done by myself along with Zachariah Aldane and Emily Maurer Provost at the University of Michigan. So to begin, the focus of this work is on improving aphasic speech recognition. Aphasia is a language disorder that impairs both written and spoken communication, and it affects roughly 2 million people in the United States alone. Now, because this disorder manifests itself in speech, automatic speech analysis provides a useful tool for clinicians, especially when it comes to remote health monitoring applications. To this end, previous work by Duke Lay has already demonstrated the effectiveness of quantitative speech analysis for characterizing aphasic severity. However, some of these speech analyses do rely on the output of automatic speech recognition systems, and this makes automatic speech recognition a bottleneck area for many downstream speech analysis tasks. Previous works by Kathleen Fraser have also shown that as automatic speech recognition performance decreases, so too does the quality of downstream extracted speech analysis features. So with this in mind, it's important that we try to optimize automatic speech recognition performance as much as possible. However, there are several challenges that make this task of disordered speech recognition hard. The first challenge is abnormal speech patterns, meaning that for aphasic speech is often dissimilar from that of healthy speech. The second challenge is high speaker variability, which means that aphasic speech is also dissimilar from other aphasic speech. And the third challenge is limited resources, in that there simply isn't as much aphasic speech data as there is healthy speech data with regards to aphasic speech recognition modeling. And all of these challenges together make it difficult to build robust automatic speech recognition models that rely on machine learning. Now, prior works that have looked at aphasic speech recognition modeling have done so in a one-size-fits-all fashion, where both aphasic and non-aphasic data is used to train an acoustic model. These works have also found that increased aphasic severity often leads to worse automatic speech recognition performance. Now, in a similar vein, previous works by Heidi Christensen have shown that using speakers which are deemed close together can ultimately lead to automatic speech recognition improvements for disordered speech. Now, a limitation of this work is that the closeness metric that is defined in their publication is based on Oracle automatic speech recognition performance. And currently, there are no works that have looked into automatically estimating this closeness for automatic aphasic speech recognition. In this work, we identify aphasic severity as a basis for closeness and hypothesize that modeling similar severity samples will ultimately yield better acoustic model performance over an acoustic model which uses all samples equally. Now, to investigate this claim, we propose the use of a mixture of experts-based acoustic model, where each expert is trained using severity. We also investigate training a severity identifier in order to select which expert to utilize at test time. In this work, we set up two experiments where the first uses an Oracle severity identifier in order to first see if having access to a test speaker's severity at test time can facilitate acoustic model improvement within a mixture of experts architecture. And our second experiment utilizes a trained severity identifier, where we predict severity at test time in order to retain a fully automatic speech recognition pipeline. Now, our automatic speech recognition architectures are shown in the slides here. Here we train hybrid HMM-DNN-based acoustic models and use feature space maximum likelihood linear regression features as our inputs. We utilize these features to attempt to build on these existing speaker adaptation methods that have worked for disordered speech recognition modeling in the past. Our baseline model that we use consists of 6 linear layers, which are trained using both aphasic and non-aphasic data, following prior works by Duke Lay. In our mixture of experts acoustic model, we have our acoustic features, which are fed into shared layers consisting of 4 linear layers. The output from these shared layers are fed into 4 experts, each consisting of 2 linear layers. Each expert is trained using varying severity, and each outputs a C-known posterior. Now, we do need a mechanism to be able to combine the predictions from all of these experts at test time. And to do this, we propose using a severity identifier. The severity identifier, which takes in acoustic features as well as X vectors as input, outputs severity probabilities. Now, these severity probabilities are then used to weight each expert's output within the mixture of expert acoustic model. Now, for all of our experiments, we utilize the Aphasia Bank dataset, which consists of 95 hours of speech data. We also utilize each speaker's aphasia quotient score in order to determine severity and segment into severity bins following that of previous work. So here, our healthy controller non-aphasic speakers are listed as healthy. Those with aphasia quotients greater than 75 are considered mild. Aphasia quotients that are between 75 and 50 are considered moderate. And aphasia quotient scores which are under 50 are considered severe. Now, in our first experiment, we hypothesized that using a mixture of experts acoustic model that is based on severity will outperform a traditional network architecture, which ignores severity. Now, to determine which expert is used at test time, we utilize an Oracle severity identifier, which assumes access to the test speaker severity in order to select the appropriate expert to utilize at test time. In this experiment, we also choose to explore different training paradigms for the mixture of experts model. Here we look at investigating the trade-off between data scarcity and severity exclusive experts. The first training paradigm which we investigate is called solo, where each expert is trained exclusively on a given severity. Now, although this approach is the most selective in terms of expert severity modeling, experts here do run the risk of having limited access to data and essentially exacerbating an already existing data scarcity problem. So our second paradigm looks to address this concern by augmenting the training data within each expert using data from our healthy set. However, if you look at experts 3 and 4 for our solo plus healthy approach, you can see that the healthy data is being added to both moderate and severe severities respectively. And that the healthy data can actually be quite distant from both moderate and severe severity classes in terms of severity. And so in this last paradigm, what we look to do is use data augmentation, but we attempt to preserve severity modeling to some extent by only using data from the neighboring severity bins. And so here, experts 3 and 4 are instead taking advantage of moderate and mild data and severe and moderate data respectively. Speech recognition performance for this first experiment is shown here, where columns in the table below represent the performance breakdown across different aphasic severities. And the rows represent the performance of our different models, which are either the baseline model or our proposed model. Now, our proposed model utilizes several different training paradigms, and within each training paradigm, we also use an Oracle severity identifier within our proposed model architecture. We compute statistical significance using a CalD bootstrap method, and we indicate statistically significant performance differences to the baseline model using an asterisk. So our first goal is to investigate whether restricting expert training data affects ASR performance. So in the case of our solo approach, we can see that using a solo training data approach for our mixture of experts ultimately leads to worse automatic speech recognition performance across all severities. However, as we move to using a solo plus healthy approach, we can see the performance gap between our proposed model and the baseline close. And this indicates that there is a data scarcity concern to consider when training a mixture of experts model. However, when we compare against our baseline model, we find that even with the augmented healthy data approach, we still find that our proposed model is underperforming in relation to the baseline model. So here we move on to using this solo plus neighbor approach, which augments data in each expert using neighboring severity bins. And we find here that the performance improvement occurs across all training paradigms, including improving our proposed model over our baseline model. So this ultimately indicates that the data scarcity concern is something that we should be aware about when modeling a mixture of experts model, but that we can still attempt to preserve severity by using neighboring severity bins when performing data augmentation. Now, in our second experiment, we train a mixture of experts using the solo plus neighbor approach that was defined in our first set of experiments. However, in this second set of experiments, we look to relax our dependence on the Oracle Severity Identifier by training a Severity Identifier to estimate this severity at test time. And now with this estimated severity identifier, we now have a fully automated speech recognition pipeline for our mixture of experts framework. One key difference to note with the predicted severity identifier is that the outputs of this severity identifier are used as probabilistic weights in order to combine the predictions of all of our experts. And this differs from our Oracle Severity Identifier, which was able to select the appropriate expert at test time. Now, our goals for this second experiment are twofold. The first is to show that we can estimate severity automatically using this severity identifier. And the second is to investigate different granularities for our severity identifier predictions. So more specifically, we look at severity predictions at the frame level and utterance level, and whether these will make a difference with how they're used within the mixture of experts acoustic model. So to answer our first question, whether we can estimate severity automatically, we output the confusion matrix for our severity identifier, where predictions are made at the frame level. Now, looking at the confusion matrix, we can see that although there does seem to be quite a bit of confusion, this confusion does seem to be localized surrounding neighboring classes. And this to us demonstrates that the severity identifier is capturing some semblance of severity. Now, also, another contribution of this error or confusion could also be attributed to the fact that the severity identifier was trained and tested using speaker-level severity labels. And this can be problematic as we're using a severity identifier which is predicting at a frame level. And as we predict at a smaller level, we could be capturing other noisy signals such as intelligibility. So our experimental results using the predicted severity identifier within our mixture of experts framework is shown here in the table. And we can see right away that when using a severity identifier that predicts outputs at the frame level, ultimately leads to our proposed model outperforming our baseline model. Now, as we move to using a severity identifier that predicts at the utterance level, we can note subtle differences between our proposed models. However, we still note the significant performance improvement over our baseline model. And what these results ultimately indicate is that by using a trained severity identifier within a mixture of experts acoustic model, we can yield performance improvements over a baseline acoustic model, which does not take severity into account. So in conclusion, in this work, we investigate the use of severity as a metric for closeness when considering aphasic acoustic modeling. We then show how this can be exploited within a mixture of experts acoustic model architecture, and we also demonstrate the trade-offs between data scarcity and severity exclusivity when training this mixture of experts model. We then show that severity can be estimated automatically using a severity identifier in order to preserve a fully automatic speech recognition pipeline. And we ultimately show that our approach yields a 3.3, 2.0, and 5.6 relative phone error rate improvement over a baseline model which does not take severity into account. So with that, I'd like to thank you for attending my presentation. And if you have any questions or comments regarding the paper, please feel free to reach me at my email listed below. Thank you.